You ever stop and think about how a stick of dynamite explodes in a flash, but a piece of iron takes, like, years to rust? I mean, they're both just chemical reactions, right? So what's going on? What's the hidden dial that controls the speed of chemistry itself? Well, we're about to find out. So here's the game plan. We're going to start with the basic question of speed itself, then look at the first big mathematical clue scientists found. After that, we'll investigate two different theories that try to explain what's happening, see how they stack up against each other, and finally, and this is the really cool part, see how all this theoretical stuff literally saves lives.
Okay, let's kick things off with something super familiar. Whether you're cooking an egg or baking a cake, what do? You turn up the heat. And we all just know, intuitively, that heat makes things happen faster. But why? What is actually going on down there at the molecular level? You know, this one simple question, it's the key. It's what unlocks the entire field of chemical kinetics. Because it's not just that things are getting hotter, the temperature is fundamentally changing the probability that a reaction will happen at all. So, how do you even begin to describe that?
Well, our first major clue comes from a brilliant chemist named Svante Arrhenius, way back in the late 1800s. He came up with this incredible equation that perfectly described the relationship between temperature and how fast a reaction goes. It was a massive deal. But here's the thing, it was like having the answer key for a math test without showing your work. It tells us what happens, but it doesn't really tell us why.
Okay, so here it is. And I get it might look a little intense with all the letters and the weird E in there, but don't worry, the idea behind it is actually way more straightforward than it looks. We're about to break down exactly what this thing is telling us.
So here's the bottom line. That K on the left, that's the reaction speed. And the equation shows us that the speed depends mostly on two things. First, EA, the activation energy. Think of it as an energy hill that the molecules have to get over. And second, T, which is just the temperature. So cranking up the temperature is like giving more molecules the energy, the oomph, they need to make it over that hill.
Okay, so Arrhenius gave us the what, but we still need the why. The first big theory trying to explain it is called collision theory. And honestly, it's just plain common sense. It starts with one simple idea. For molecules to react, they have to physically smash into each other. Right? Makes perfect sense.
But, and this is a huge but, just bumping into each other isn't nearly enough. Two things absolutely have to be true. First, they need to collide with enough force to get over that activation energy hill we just talked about. A little tap isn't going to cut it. And second, they have to hit each other in the perfect orientation, like two puzzle pieces clicking into place. Now think about what that means. The vast majority of collisions that are happening all the time, they're total duds. Nothing happens. The molecules just bounce off each other and go about their day. It's only a tiny fraction of all those crashes that are actually successful. And that right there explains why reactions aren't always instant.
But collision theory has a bit of a weakness, an Achilles heel. To get its predictions to actually match what happens in the real world, especially with big, complex molecules, scientists had to tack on this thing called a steric factor. And really, it's kind of what it sounds like. A bit of a fudge factor to paper over the fact that a simple yes or no on the orientation isn't the whole story. And that weakness leads us to a much more powerful idea.
All right, let's bring in our second theory. This one is called transition state theory, and it takes a totally different approach. It doesn't just focus on the start and the end of the collision, it zooms way in on that one critical, fleeting moment of transformation itself.
This image right here perfectly captures the idea. Just think of a reaction as having to climb over an energy hill. The reactants are at the bottom on one side, and the products are waiting on the other. That activation energy, that's the height of the hill. And the transition state is that single, unstable point right at the very top. And this transition state is just mind-blowing. It's not a reactant, it's not a product, it's this bizarre, super high energy, unstable mashup of both, where old bonds are breaking and new bonds are forming at the exact same time. And it exists for, get this, 1/100th of a trillionth of a second. It is the absolute point of no return. From the top of that hill, you either tumble forward to become products or you fall back the way you came.
So now we've got our two main contenders, the simple, straightforward collision theory and the more complex, but powerful, transition state theory. So how do they really stack up? Which one gives us a better picture of reality? Let's put them head to head. As you can see, collision theory is great because it's simple and easy to grasp, and it works pretty well for basic reactions with simple gases. But transition state theory is just on another level. Its secret weapon is that it deals with something called entropy, which is basically just a fancy word for disorder. See, forcing two molecules into a very specific ordered arrangement at the transition state is tough, and that can slow a reaction down. TST can actually calculate that effect, while collision theory just uses that steric fudge factor to gloss over it.
Okay, I know this might all seem super abstract and theoretical, but trust me, understanding and controlling the speed of reactions is absolutely fundamental to our entire modern world. From making plastics to designing life-saving drugs, this isn't just for exams, it's incredibly practical.
You see these massive industrial reactors? The engineers running them are basically playing with these exact principles all day long, tweaking temperature and pressure to get the reaction speed just right. Doing it correctly means you can efficiently make everything from fertilizers to the materials in your phone. Get it wrong, and it's wasteful, expensive, or even dangerous.
But, you know, you don't actually have to go to a giant factory to see the most sophisticated, most efficient chemical reactors on the planet. Nope, you just have to look in the mirror. We've got trillions of them inside of us, working every single second. They're called enzymes.
Enzymes are nature's catalysts. They're biological machines that grab onto specific molecules and make reactions happen millions of times faster by lowering that activation energy hill. But just like any machine, they have a top speed, a Vmax. You can see it on the graph. The speed shoots up at first, but then it just levels off. Why? Because the enzyme is totally swamped with work. It's physically saturated and can't go any faster.
Now, biochemists have a clever way of looking at this data called a line-waiver-Burke plot. I know, it looks a little weird, but all it does is turn that curve we just saw into a nice, straight line, which is way easier to analyze. So this green line here, in panel A, that's our baseline. That's a normal, healthy enzyme, just doing its job. But what happens when we throw a wrench in the works? And this is where it gets real. We're talking life or death stuff, like antifreeze poisoning. The poison in antifreeze gets converted by an enzyme in our liver into something even more toxic. So what's the antidote? Believe it or not, a shot of medical-grade ethanol, alcohol. Why on earth would that work? Well, it's a perfect example of something called competitive inhibition.
Okay, let's break down this incredible piece of biochemistry. The enzyme responsible is called alcohol dehydrogenase. And it turns out this enzyme actually prefers ethanol. It binds to it way more tightly than it binds to the antifreeze. So by flooding the patient's system with ethanol, doctors basically gum up all the enzyme's machinery. The enzymes get so busy dealing with all the ethanol that they can't touch the poison. It's this brilliant chemical distraction that buys the body precious time to get rid of the antifreeze safely.
And the story doesn't even stop there. There's another, more sinister way to shut down an enzyme. Molecules called non-competitive inhibitors. They don't play fair. They don't compete for the main active site. They sneak around to a different spot on the enzyme, bind there, and change the enzyme's whole shape, which just breaks it. As you can see in panel C, it totally changes the kinetics. This is how many deadly poisons, like cyanide, work. They shut down the essential enzymes that help our cells breathe.
So when you step back and look at it, we've gone from a simple question about cooking an egg all the way to the complex molecular dance that can literally save a person's life. This ability to understand, to predict, and to control the speed of chemistry gives us incredible power. It's the foundation of so much modern medicine and technology. And it just makes you wonder, with this kind of control, what are the next big problems we're going to solve?